In the last few classes, we have formulated the principle of WKB method. We have derived an expression, a general expression for the WKB wave function, and we have encountered the suitable situations where WKB can be effectively applied. As a consequence of this idea, we have also identified that the WKB wave function will be represented by a cosinusoidal or sinusoidal oscillation in classical region and will be represented by means of either a decreasing or increasing exponential term in a non-classical region. The way in which these solutions in the classical and non-classical region are connected are also analyzed under the title The Connection Formulae. And we have seen that the wave function represented by a sinusoidal oscillation in the classical region will be modified or will be transformed as a decreasing exponential term, with the constant multiplying the decreasing exponential term being half, or conversely the constant multiplying the sinusoidal oscillation being twice the constant multiplying the decreasing exponential term. Also, the wave function represented by a cosinusoidal oscillation in the classical region will be transformed as an increasing exponential term in the non-classical region with no modification for the constant multiplying both of these wave functions. So now onwards we will start harvesting these crops under the title Applications of WKB Method. As per the demand of the syllabus, we will have to apply the WKB method to bound systems or to bound state, or to evaluate the energy eigenvalues of bound state and if possible the state function as well. And in this title itself there can be a few specific examples like harmonic oscillator, the hydrogen atom problem, or the particle in a box problem, etc. And we will discuss the applicability of WKB method to a purely quantum mechanical phenomenon, the theoretical aspects of the same that you have already studied and applied in the case of analyzing alpha decay and the working mechanism of a tunnel diode, etc. And this phenomenon is referred to as the quantum tunneling or quantum mechanical tunneling. So first of all, let's consider the bound state. A bound state is a system, of course, a quantum mechanical system that is bound to an attractive potential. So the case can be a central potential problem, even though we state that these are quantum mechanical systems or subatomic systems or microscopic systems. You can consider or you can analyze the quantum mechanics possessed by heavenly objects that are subjected to the central potential referred to as the gravitational potential. So this can also be applied, or in this case also the WKB method or quantum mechanics can be analyzed or could be applied. Now, first of all, we will consider a general treatment of the bound system or a bound state. A bound state, as I have told you, is a system that is permitted to perform its dynamics under an attractive potential, so that the system is assumed to be in a state of stable equilibrium. The most general case of such a potential to which a system is subjected can be graphically represented like this. Along the horizontal direction, we represent the position coordinates, say x, and along the vertical direction, of course, we represent the energy. The total energy of the system, as you know, is a constant and is represented by a line parallel to the x-axis. And the potential energy to which such a bound system is subjected may be most suitably represented using a curve like this V of x. And this can be a central potential as well, as in the case of electrostatic potential or magnetostatic potential, or the potential to which heavenly objects are subjected, that you have discussed in Kepler problem, in classical mechanics, etc. For the sake of convenience, I will be taking this as the nature of this potential, and this, as you know, is the potential to which a harmonic oscillator may be subjected. But I am not telling you right now that it is the potential to which a harmonic oscillator is subjected. This is in fact a potential to which a bound system is subjected. Now look at this figure. You can have two different points. I will label these points, say respectively x1 and x2, at which the total energy curve meet the potential energy curve. Definitely, these are nothing other than the classical turning points. So, I have a turning point at the coordinates, say x1, and another one at the coordinates, say x2. We assume that, of course, these two turning points will be dividing the entire region in space to which the system can have a dynamics into three. These are labeled as a region 1, region 2, and region 3. Both region 1 and 3 are having the potential energy exceeding the total energy. So these two regions are non-classical regions, whereas in region 2 the total energy exceeds the potential energy. So that the region 2 is purely a classical region. And in this region, we know that if you are going to disturb the system that is occupying, say, a position coordinate, say, somewhere here, any kind of a disturbance will be imparting a restoring force upon the system, and the system will have a tendency to return back to its equilibrium position. As a consequence of the inertia, it will overshoot the equilibrium position and will be going to the other side. This will account for an oscillatory motion for the system in the region 2. And such a wave function in the WKB limit can be represented using either a cosinusoidal oscillation or using a sinusoidal oscillation. However, you cannot have such a flexibility of taking such a choice in this particular case because we have already seen the connection formally. How it happens, so I'll come across it very shortly. Now look at region 1 and 3. These are non-classical regions, and classically, there is no probability for finding the particle in region 1 or in region 3. However, quantum mechanically, there exists a finite probability. But as you move away from these two turning points in region 1 and 3, the potential energy will be largely exceeding the total energy, so that the probability for finding these particles will be going on diminishing rapidly as you move away again and again from the turning points in both regions 1 and 3. And such a probability will be always represented by a decreasing exponential wave function. So the wave function representing the system in region 3 and in region 1 are decreasing exponential wave functions, and these wave functions are being written using the WKB format as phi1, the wave function representing the system in region 1 as A1 by root P, where A1 is the normalization constant, as you know, e raised to minus 1 by h cross integral x to x1 p dx5. Take care of the limit. I'll be taking this as a positive limit, integral x to x1, where x is an arbitrary point in region 1, x1 is greater than x, so that x to x1 happens to be a positive limit for integration. And in region 3, the arbitrary choice of point x will be, say, somewhere here, and we will have to take the integration from x2 to x as a positive limit. It is in that manner we have formulated the connection formally. So phi 3, the wave function representing the system in region 3 is a3 by root p e raised to minus 1 by h cross integral x2 to x p dx prime. If you forcefully take this integration from x to x2, this turn out to be an increasing exponential wave function. That's an error that you might encounter if you do not take care of this limit of integration. So both these wave functions are decreasing exponential wave functions, and I have made the point clear that in region 1 and 3 the wave function needed to be decreasing exponential terms. Now in region 2, using the connection formulae, you can write the wave function, either connecting the nature of the wave function in region 2 with the wave function in region 3 which is already known, or with the wave function in region 1 that is also already known. So you have two different choices of representing the wave function for the system occupying region 2. That is, write the wave function applying the connection formula to the wave function in region 3, or follow the same procedure for the wave function in region 1. Let me write it using the wave function in region 1. Wave function in region 1 is decreasing exponential. A decreasing exponential wave function in the non-classical region is to be replaced by means of a sinusoidal oscillation with this additional plus pi by 4 term, with this integration being, say, a positive limit, and the constant multiplying the sinusoidal oscillatory wave function needed to be twice the constant multiplying the decreasing exponential term. So I have put a 2 multiplication factor here. A1 is the constant or coefficient for the decreasing exponential, so here the constant needed to be 2a1. By root p is retained sine of 1 by h cross integral x1 to x. I am connecting the wave function in region 1 in order to obtain the wave function in region 2. So the connection should start from x1 as the origin being taken, x1 to an arbitrary choice of points, say x, in between x1 and x2, as long as the connectivity to wave function in region 1 is concerned. That is exactly identical with the wave function being written by connecting the wave function in region 2 with region 3. Again, in region 3, the wave function is decreasing exponential, so it is to be replaced, or it is to be transformed to a sinusoidal oscillation, and the constant being multiplying the sinusoidal oscillation must be twice that of the constant multiplying the decreasing exponential term. So I have put 2a3 by root p sine of 1 by h cross. Here I am connecting the wave function to the turning point, say x2, and the arbitrary choice of point, say x, is somewhere here. So the integration limit will be from x to x2 as long as the connectivity of wave function in region 2 with that in region 3 is concerned. That is being put as a integral x to x2 p dx prime plus pi by 4. Now, of course, 2 will be vanishing and root p in the denominator also will be vanishing. A1 I can take it to the right side and I will make some arrangement for this integration. See, I have integral x1 to x p dx prime on the left side and x to x2 p dx prime on the right side. And the constant part that I can have is integral from x1 to x2. So I'll have to incorporate integral x1 to x2 p dx prime with this term or with this term. Let me do it for this term. That is, integral x1 to x2 p dx prime is integral x1 to x p dx prime plus integral x to x2 p dx prime, provided x is in between x1 and x2, and I have this choice of x in between x1 and x2 as long as region 2 is concerned. So that we substitute integral x1 to x p dx prime as integral x1 to x2 p dx prime minus integral x to x2 p dx prime, taking this term to the left side. That is being substituted here. A1 is retained for one more step. A1 sine of 1 by h cross integral x1 to x2 p dx prime minus integral x to x2 p dx prime plus pi by 4 equal to the right side is retained. Now I'll be opening this bracket and I require this term as well. Now look at the right side of this equation. Sine function has an argument 1 by h cross integral x to x2 p dx prime plus pi by 4. On the left side you can have this term integral x to x2 p dx prime plus pi by 4, but this is minus. So if I can have a minus pi by 4 here, I can take minus sign common from this term and pi by 4 to make overall minus of this term plus pi by 4. That is exactly identical with this one. So let me add and subtract a pi by 4 here. So this will give me plus pi by 4 exactly behind this minus sign, and say minus pi by 4 exactly or immediately after this integral p dx term. Now this may be written as say 1 by h cross within the argument. Yeah, of course I'll take a1 to the right side for this step. What remains is sine of 1 by h cross integral x1 to x2 p dx prime. I have a pi by 4 here plus pi by 4 here, making it say plus pi by 2. Minus is taken as a common factor for this term and this term to make it overall minus of 1 by h cross integral x to x2 p dx prime plus pi by 4. That's equal to a3 is already there, a3 by a1 sine of 1 by h cross integral x to x2 p dx prime plus pi by 4. Now this equation is of the form sine of an angle, a constant angle, because integral x1 to x2 p dx prime will be a constant as it is over say one half of a complete oscillation. If I am start counting the oscillation at this point, from this point to this point it's half an oscillation, and once it return back it will be completing the oscillation. So from x1 to x2 I can have this integration over half of the oscillation or half of the period as long as time domain is concerned. So this is overall sine of a constant angle. Say I will write it say sine n pi because there is no change for the function, and from my plus 2 knowledge I know that the function will be changing from sine to cosine or vice versa, or from tan to cotangent or vice versa, or from cosec to sec or vice versa in the odd multiples of pi by 2, and in even multiples of pi by 2, or say or the integer multiples of pi, there is no change for the function. I have sine function on the left side as well as on the right side. So this might be an integer multiple of pi, n pi minus theta is equal to, of course there is a constant on the right side, I have a constant part, into sine of this angle say theta. This is what you call the reduction formulae for theta, or reduction formulae for pi minus theta, and this equation resembles this fundamental equation in trigonometry. So I need to be take care of what is to be written as the format of the equation. So this is of the form sine of n pi minus theta equal to some constant into sine theta, and this constant must turn out to be a power of -1, because in some quadrants the sine function will be negative and in some quadrants sine function will be positive, and the only scope for this constant needed to be -1 raised to a number. And this reduction formula is nothing other than that for n pi minus theta. We know that sine of n pi minus theta equal to -1 raised to n minus 1 sine theta, where n start from 1 only. However, I have a general expression for sine minus theta which is equal to sine theta. If I am interested, I can incorporate that also by modifying this equation. So when n is equal to 1, this is sine pi minus theta. Sine pi minus theta is an angle falling in second quadrant, and in second quadrant all except sign are negative, so sign is positive. That is why I can have say minus 1 raised to 1 minus 1, that is 0. Minus 1 raised to 0, which is 1, that is the constant part, sin theta. When n is equal to 0, here also this is satisfied. When n equal to 0, this is sin minus theta, that's equal to minus 1 raised to 0 minus 1, that is minus 1. Minus 1 raised to minus 1 is minus sin theta. But he'll be writing it more conveniently starting from n equal to 0 if I put this from say n plus 1. So instead of using the reduction formula for pi minus theta as such, I'll be making use of the reduction formula for pi minus theta with the coefficient being say n plus 1. Sin n plus 1 pi minus theta is minus 1 raised to n sin theta. When n is 0, this is sin pi minus theta equal to minus 1 raised to 0, which is 1 sin theta. So this is also true. Let me make use of this equation because this will give me values starting from 0 onwards. This value 0 is also significant. That will give you a wonderful result towards the end of this discussion. And this is a very fundamental result in quantum mechanics, which is different from that in classical mechanics as well. So that is why I'll be making use of this one. So comparing this equation with this standard equation, I have sine function and this part should be identical with this angle n plus 1 pi minus theta. So theta correspond to this one. Theta will be there on the right side as well. So clearly a3 by a1 is nothing other than minus 1 raised to n. And this part should be equal to n plus 1 pi. So a3 by a1 is minus 1 raised to n. Now I am interested in this one. That will give me some wonderful results. 1 by h cross integral x1 to x2 pd x prime plus pi by 2. Okay, let me take plus pi by 2 to the right side. So this quantity equal to n plus 1 pi is already there on the right side. Plus pi by 2 upon coming to the right side become minus pi by 2. So pi is common, that is taken out. What remains is n plus 1 minus half. N plus 1 minus half is n plus half. N plus half pi. This half, as you may guess right now, or if you are interested, you will be definitely guessing this corresponds to the 0 point energy of this kind of systems, and you can have this formula if and only if you compare with this one. That is why I have taken a modified for reduction formula for 180 minus theta, or say pi minus theta. So 1 by h cross integral x1 to x2 pd x prime is equal to n plus half pi. That is integral x1 to x2 pd x prime equal to n plus half pi into h cross. H cross is taken to the right side. That is integral x1 to x2 pd x prime equal to n plus half. H cross is h by 2 pi, so pi vanishes. This is half h. Let me multiply this equation by 2 because I am not interested in these 2 on the denominator of the right side. So this becomes 2 integral x1 to x2 pd x prime equal to n plus half h. But twice this quantity is this one plus this one. So integral x1 to x2 pd x prime plus integral x1 to x2 pd x prime equal to n plus half h. That is integral x1 to x2 pd x prime. We make use of the result. If you change the limits from upper to lower, you will have to put a minus. Integral, so minus is put here. Integral x1 to x2 is modified as integral x2 to x1 pd x prime. What does this means? Integral x1 to x2 pd x prime, you are evaluating the integration from say x1 to x2. So x1 to x2 is the positive movement direction. Minus integral x2 to x1 pd x prime means you will be returning back like this. Dx in this case is negative. So minus and this dx negative will be absorbing to make it say positive upon your evaluation. So this include integration from x1 to x2 and back. That include the integration over a complete cycle or a complete period of operation as long as the bound state or bound system is concerned, and is represented by a closed integral. So closed integral pdx equal to, there is no modification for the right side other than the vanishing of these two. So all these terms will have the same right side, n plus half h. For closed integral pdx equal to n plus half h. This is the result that we obtain for the bound state. Closed integral of momentum, and this momentum can be written as p equal to square root of 2m into E minus V, where E is the total energy. What is so significant with this total energy? Potential energy will be always known to us, or in general, at least in the case of non-problems, the potential energy will be known. Or once you know the potential energy, then only we will be going behind such a quantum mechanical system. And our primary aim is to evaluate the energy eigenvalue. You have the energy eigenvalue in this expression. So this evaluation will definitely give you a method of evaluating the energy eigenvalue of the system under our study. That is the prime important parameter as long as a quantum mechanical study is concerned. So this is the fundamental result that you can have as long as a bound system is concerned. Closed integral of momentum over one complete cycle or over one complete oscillation or over one complete period of time domain is equal to n plus half h. This corresponds to the Bohr-Sommerfeld quantization rule of the old quantum theory. Bohr-Sommerfeld quantization rule, or the modified Bohr-Sommerfeld quantization rule, which is in fact a manifestation of the Wilson-Sommerfeld quantization rule. Wilson-Sommerfeld quantization rule is integral pdx over one complete cycle of dynamics equal to n times h. Half is not there in Wilson-Sommerfeld quantization rule. However, in Bohr-Sommerfeld quantization rule, you can have this half corresponding to the 0-point energy. And in the modification for the reduction formula for 180 minus theta, I have told you that it will be starting from 0 onwards. When n equal to 0, this energy must correspond to half h times some constant that you can have upon the evaluation of this integration. So this gives you a better approximation and a better result, or a more quantum mechanical result as long as the mathematics is concerned. And it's an important question as long as your examination also is concerned. There are only one confusion about this topic as long as the question setter is concerned. That is whether this is to be kept in short answer or in essay or in problem. So take care of this fellow. This is referred to as for this rather than referring. There is a little modification for Bohr-Sommerfeld quantization rule. This corresponds to the Bohr-Sommerfeld quantization rule of the old quantum theory. And the instrumental part of this formula is that this gives you a mathematical tool for evaluating the energy eigenvalue of the system under your study. Now we have started with the wave function, so we'll finish the story that the wave function will be able to tell us. The wave function representing the system in region 2. Why don't you take the wave function representing the system in region 1? Because in region 1 you cannot expect such a bound system. Bound system will be limited within the boundary of this potential in terms of the fact that in the region where the potential energy is less than the total energy. Of course, there is a probability for finding the system beyond this limit, which is a quality of the or a property of the quantum mechanical wave function. So most often you can have a greater probability for finding the system in this region. That is why we are interested in the wave function in this region 2. So phi 2 is equal to 2a1 by root p sine of 1 by h cross integral x1 to x pd x prime plus pi by 4. Normalization require norm square equal to 1. So squaring this or taking the scalar product of this one with itself, you have 2 into 2, 4 a1 square by root p into root p, that is by p is written here sine square. I might not have made this kind of an argument. Sine square will have an average value over half a cycle. That we know that the integral of sine square over half a cycle is 1 by 2. Anyway, I have repeated this here. For a1 square integral x1 to x2, sine square is 1 minus cos twice this angle. So 2 might be there. Anyway, how not put it's 2 twice the angle. The quantity within the bracket is nothing other than say this one, dx by 2p is equal to 1. Now we will be integrating this in two different terms, integral 1 by 2p dx minus integral, of course this constant part is there common, minus integral x1 to x2 cos twice an angle dx by 2pi. But integral of cosine over half a cycle or from x1 to x2 will be 0, so that term will be going, and what remains is for a1 square integral x1 to x2 dx divided by 2p, that's equal to 1. Now we know that the momentum is mass times velocity dx by dt. So dx vanishes, what remains is dt divided by m, which is being put here. For a1 square integral 2 is there 1 by 2 dt divided by m, that's equal to 1. 2m is also constant that are taken out for a1 square by 2m. Integral dt is t. In the limit from x1 to x2, if it is from x1 to x2 and back, that will be completing a period, say tau. So it is from x1 to x2 only, then it is half a period, that is tau divided by 2, that's equal to 1. I have not modified any of these numbers. For a1 square tau divided by 2m into 2, that's equal to 1. Clearly a1 square is equal to m divided by tau. 4 and 2 into 2 will be vanishing. For a1 is equal to m omega divided by 2 pi, since the period t or tau equal to 2 pi divided by omega. 2 pi by omega is there on the denominator, so that the reciprocal will be coming to the term as omega divided by 2 pi. So a1 equal to m omega by 2 pi raised to half. So that our wave function becomes 2 by root p. Instead of a1 we have the substitution m omega by 2 pi raised to half sine of 1 by h cross integral x1 to xp dx prime plus pi by 4. That is 2 is there outside this square root. Let me take it inside. The one of the 2 will be then cancelling with that in the denominator. 2m omega divided by root p is also taken. Pi p raised to half sine of 1 by h cross integral x1 to xp dx prime plus pi by 4. This will give us a better representation for the wave function representing the harmonic or say a bound system. Now I have two corollary results to be shared with you. In the derivation of the Bohr-Sommerfeld quantization rule, we have taken two translucent boundaries as the turning points at say x1 and x2. Translucent in the sense that the particles are able to penetrate into the boundary or beyond the limits of the boundary. Though the probability will be falling very rapidly. See, these are represented by means of an exponentially decaying wave function. The nature of exponential decay, as you know, will be very rapid. If it is, say, having a value 10 raised to 5 at a particular point of position, in the very immediate position, this will be turning to 10 power 4. In the very next immediate position, this will be turning to 10 power 3. From 1 lakh to 1000, it requires an infinitesimally small thickness to be say penetrated. Though this is the nature, there exists a probability for finding them beyond the boundary, though it is extremely smaller. This indicates that the particle always will have a tendency to penetrate into the boundary, and such a boundary is what you call a translucent boundary rather than a rigid or an opaque boundary. See, translucency and opacity are something related with light, and we are talking about particles, and this difference is already known to you. Light also consists of particles, and in quantum mechanics we specifically talk about this kind of systems. Suppose the boundaries are not translucent, these are rigid. Both these boundaries are rigid, as in the case of, say, classical problem that we have studied, that is the case of a particle in a box problem. The Bohr-Sommerfeld quantization rule is a little different. If both the boundaries are rigid, then the equation that will help you to evaluate the energy is given by integral x1 to x2. See, here I am not taking a closed integral. Integral x1 to x2 p dx prime is equal to n pi h cross p dx prime equal to n pi h cross. And suppose one of the wall is rigid and the other one is translucent, then you will have this equation modified as integral x1 to x2 p dx prime equal to n plus 3 by 4 pi h cross. So these results are also used or are usable under suitable experimental situations. Now we will see a case of bound system. Here also we take our classical example. Some of you might have made friendship with this fellow, that is harmonic oscillator. Even in this semester itself, you have seen the case of harmonic oscillator as a case of perturbation problem or as a case of variational method. Now in WKB also we will encounter this fellow, the case of harmonic oscillator. I am not going to represent the Hamiltonian. I am writing here only the potential energy to which the harmonic oscillator is subjected, that is half kx square, where k equal to m omega square, where with m being the mass of the oscillating system. Now to apply WKB method, of course our primary aim is to evaluate the energy eigenvalue, and the key for this evaluation is the Bohr-Sommerfeld quantization rule. As this potential is half kx square, it represents, say, two different points having the same potential symmetrically on both sides of this equilibrium positions. There can have a couplet of points having the same potential energy, as this curve is a parabolic curve. And there could be two extreme points where, say, the potential energy will be meeting the total energy, and the displacement corresponding to these points, you call them the amplitude or the maximum amplitude. If you take this as a plus A, you will have to take this as a minus A, under the assumption that the origin corresponds to the equilibrium position. So I require these two extreme points, as these points happens to be the limits of integration as long as the Bohr-Sommerfeld quantization rule is concerned. For that, I'll have to take the condition for turning point. It is the point at which the total energy meets the potential energy. That happens when half kx square or half m omega square x square is equal to total energy E. That means x square equal to 2e by m omega square, and I'll represent this constant point as, say, A, and I can have two different choices for A having the same magnitude, A equal to square root of 2e divided by m omega square. Now look at the Bohr-Sommerfeld quantization rule. I am writing it not as the closed integral from minus a to a in p dx prime equal to n plus half h, with p being root 2m into e minus v equal to n plus half h. Now integral from minus a to plus a integral from minus a to plus, here I might have put, say, this as closed integral. See, the closed integral result is used. This is an error. A and minus a might not be here. So this is 2 times integral from minus a to a, root of 2m into e minus 2m into v. Instead of v, I have put a half m omega square x square dx. The right side is retained. This is now twice integral minus a to a, 2m into e. E from this expression is nothing other than half m omega square a square. So we can put e as half m omega square a square. Half vanishes, m becomes m into m square omega square a square, minus 2 vanishes, m square omega square x square dx equals n plus half h. Now twice integral minus a to a, integral from minus a to a can be written as, say, 2 times integral from 0 to a in magnitude. So that 2 with these 2 make it, say, 4. M omega is a common factor for this square root. M square omega square is taken out, and out of the square root we will have m omega. Integral from 0 to a, root of what remains is a square minus x square dx equals n plus half h. That is for m omega. Either you can put x equal to a sin theta here. X can be put as, say, a sin theta, x equal to a sin theta. The limits of the integration then needed to be changed. When x is equal to 0, sin theta is equal to 0. That means theta equal to 0. When x equal to a sin theta equal to a vanishes, sin theta equal to 1, theta is then pi by 2. And you can put this as, say, a square into 1 minus sin square theta, that is a cos theta, and can be integrated. But I recall this result, integral from integral root a square minus x square is a square by 2 sin inverse x by a. So let me use that flexibility. I have evaluated this integral a square by 2 sin inverse x by a in the limit 0 to a equal to n plus half h. For m omega by 2 a square. See, look at this expression. A square is nothing other than 2e by m omega square. So it is written here 2e by m omega square. Because I am interested in evaluating the energy eigenvalue. So on the left side, I will have to obtain somehow, say, energy E into sin inverse x by a. Upon giving upper limit, say, sin inverse a by a, sin inverse 1, that is pi by 2, minus sin inverse 0, which is 0. That's equal to n plus half h. Now 2 into 2 vanish with this 4. M omega vanish with this m and omega square. Take 2 pi to the right side. E is retained on the left side. Take omega to the right side to make the expression for energy or the evaluated energy as E is equal to n plus half h divided by this 2 pi is here. H by 2 pi is written as h cross. Omega is taken to the right side, say, to make the expression for energy, general expression for the energy of the nth quantum state of linear harmonic oscillator as n plus half h cross omega. This also gives us the 0 point energy corresponding to n equal to 0 as, say, half h cross omega. So WKB could be effectively applied in the case of the linear harmonic oscillator problem, and we have obtained the result that is purely a quantum mechanical result, though we have seen it several times. With that, let me conclude our discussion on bound state. A few assignments for you. I have some corollary results. Assignment 1. You prove those corollary results. You can refer Applications of Quantum Mechanics by Nuruddin Zetali. Now assignment number 2. Apply WKB method to evaluate the energy of particle in a box problem. Assignment number 3. Do the same for hydrogen atom problem. These are important. You can have a problem question for your examination coming from this Bohr-Sommerfeld quantization rule. All these problems are discussed in the standard textbooks. You can refer those textbooks as well and try to timely submit your assignments.